like this. My first question for you is, do you think this is a function? You would say no. And Ian, why is this not a function? Can you give me a quick 3-letter answer?
I don't know about a 3-letter answer,
What will you
but
just,
using like the vertical asymptote rule, multiple x values per y or whatever.
right. The 3 letters I was looking for was called the vertical line test. So you just basically describe the vertical line test to me, right? Like if I take a vertical line here like this, then it kind of has one x value has 2 y values, right? So it's not a function. It fails the vertical line test. Okay. But here's the interesting thing, my friends. We all agree this is not a function. But if I look at this point right here, could I talk about the slope of the tangent line? I think I could. I think if I asked you guys to draw a sketch of the tangent line, that tangent line might look something like this. And this, I could even do the same thing right here. I think this tangent line looks something like this, roughly speaking. Does that make sense? So like, I mean, they should actually be mirror images of each other. So that's, let me redraw it. Yeah, I give up. Something like that. Okay. So my point is that we can still talk about the slope of the tangent line to the curve. However, let's pretend that this point here is equal to 1/2, just for example. I can't just say, what is the slope at x equal to 1/2, right? I can't answer that. Why can I not answer that? Because there's 2 slopes at x equal to 1/2. So, we can't answer this. Unless they also give us the y value. Okay. So if I look at this curve right here, this is not a function, but you know what? I can still talk about the slope of the tangent line. Just x equal to 1/2 is not enough because there's 2 answers. But they say, oh, what's the slope at 1/2 rad 3/2? Oh, then there must be talking about this point. I can give you this slope. If they say, oh, what's the slope of 1/2 negative rad 3/2? Then they're talking about this slope right here. So in this case, they have to give me both the x value and the y value, right? So I need x value, but they also must give me the y value. So when you look at something like this, overall, this is not a function. But if you look locally right here, only at this piece, this part is a function. If you just were restricting yourself to this piece. If you were just looking at this piece right here, it looks like a function. So if we go to our class notes, when we can write something as y equal to, that defines y explicitly. Explicit means I'm telling you very directly what the function looks like. If I embed my y inside of an equation, then it's not y equal to something, it's y is involved in some expression, in some equation. So that means that y is defined implicitly. Now, in this case, I could solve for what y is by adding x squared to both sides. But in something like my example over here, in this example, this is x squared plus y squared equal to 1. Y is treated as a function that's implicitly defined. That is implicitly defined. So the word implicit, that has the same root as the word imply, right? It's like imply. And imply means to suggest. You're not saying it directly, you know. You're not saying, I don't know, all the examples I can think of are rude. Anyways, you can suggest something without saying it directly. You know, you could like, what's something positive? Like, I don't know. I can't think of an example right now. Something like, oh, instead of saying, oh, you're beautiful, I'm in love with you, you could say something like, oh, I really like your new haircut. I'm implying, I don't know, that's not a good example, but you can imply stuff, right? So that's what we're doing with this equation. We're implying that y is a function, but it's not y equal to something, it's buried inside of an equation, okay? So really, this section is called implicit differentiation, and we're just, we're basically working with derivatives of functions that are really kind of contained inside of an equation. And the name of the game is to really treat y as a function of x. Okay, so I'm going to highlight that part right here. We treat y as a function of x. So I have this like 4-step process for how we're going to do implicit differentiation. And a lot of my students are really good at step 1, but steps 2 through 3, which is the algebra part, this is the part that actually trips students up more than the calculus part. This part is algebra. So let's take a look at an example.